Hi, we're going to see today how to solve situations that requires optimization, and essentially it's an application of differentiation of functions that we can use in many situations. So every time you have a function and you want to maximize this function or you want to optimize the situation, you usually use derivatives and differentiation to optimize. So I'm going to show you this with an example. This is a typical example in many books, in many websites. For example, it's in Paul Dawkins' notes for differentiate functions. I'm going to post the link in the video down for you to learn more about differentiation from other sources. And basically, this is the idea of the exercise. What you can see here is a circle, and inscribed on the circle is a rectangle. Okay, so the idea is to find the rectangle. You can see here the rectangle. So here are the vertices of the rectangle, and the diameter of the circle we're going to say that is 2. Okay, so diameter of the circle is 2, and we're going to find what are the dimensions of the rectangle whose area is maximum. Okay, so we're going to find the maximum area on the rectangle with this maximum area. First thing you have to do every time you have an optimization situation is to find a way to connect the function that you need to maximize with the dimensions or the variables that you have involved. In this case, it's asking us about dimensions and area. So it's pretty easy to know that the area of the rectangle is just base times height. Okay, so you just need to go to a geometry book and check what are the dimensions, how to calculate the area of a rectangle, and calculating the area of the rectangle, you know that is the base times height. So just for you to know that the base will be this distance and the height will be this distance over here. Okay, so now basically we have a function area that depends on 2 dimensions, base and height. So the best way in an optimization problem is to find something that we call a constraint. Okay, and what is a constraint? A constraint is just an equation that links 2 of the variables in order just to have one. In this case, our constraint, we need a constraint between height and base. Okay, and we can do it here using the fact that the circle is diameter 2. So you can see here that using Pythagorean theorem, b squared plus h squared equals diameter to the second power, or 2 to the second power. So in this case, I'm just going to erase it. It will be 4. So right now, what we have found is how to get the height in terms of base. And now we can have just the area as a function of just one variable. So what I'm going to do is to solve one equation for base or height and then set it in the equation for area. So let's see how to do it. So essentially I'm going to solve this for h. So let me check here. I'm going to subtract by b squared. Okay, so what I have is h squared equals 4 minus b squared, and now I'm going to take the root of h squared. We're going to use just positive roots because obviously those are lengths, so lengths cannot be negative. and we have the height in terms of the base. So now that you have the height in terms of the base, we're going to set it on the other equation. So we have that the area is going to be base times height, but the height is going to be root of 4 minus b squared. Okay? So right now what we have is just a function. Area is going to be a function of just one dimension, the base. And now we need to find the maximum area. To find the maximum area, you have to differentiate this function. So we need to find out the area dB. And the question is how? How would you get the area in terms of b? So actually it's pretty simple if you know the rules of derivation. There's a video in my YouTube that explains an example in which we apply the rule of multiplication and the rule of division. So I'm going to show you how to apply it. So this will be rule of product. You can see here that b is multiplying this root. So I'm going to define this value of the root. I'm going to say that is b, and b I'm going to say that is u. So essentially what I just did is to put that the ADB is going to be u times b, the u times b, so it will be the u db times b plus u times dv db. Okay, so this is what we have to do. So we need to find out du db and dv db. Okay, some sound, no problem. So now let's set u is going to be equal to b, right? So the u db is going to be the derivative of b, that is 1. And now the db is going to be first b is going to be root of 4 minus b squared. So we need to differentiate, right? So dv db is going to be the root of the derivative of the root. So derivative of the root is 1 over 2 root of the argument 4 minus b squared multiplied by the derivative of the argument. Derivative of 4, 0, derivative of negative b squared minus 2b. Okay? Remember to use your table for derivatives if you have no idea how to do it. So bear in mind to have the table of derivatives with you, because in this way you will know how to differentiate b, how to differentiate the root of b, how to differentiate b squared. Okay? Just a reminder. So now we have these derivatives, we just need to apply them into the equation. So we're going to apply it into this equation. So what we're going to do is just the a db, or derivative of area 2 length, will be du db 1, so 1 times b root of 4 minus b squared minus or plus, look at, I can simplify here the 2, plus u, that is b, times minus b over root of 4 minus b squared. Okay, so I'm going to simplify it a little bit. The a db is going to be 1 times this root of 4 minus b squared, plus, minus times plus, negative, b squared over root of 4 minus b squared. Okay, so basically this is what we have. We have this expression, and to answer our question, that is to maximize the area, we need to set the derivative equals to 0. So remember that when you set the derivative equals to 0, means that you're talking that the area is maximum, or you're telling that the area is a minimum. Okay, you have these two choices. So now we're going to set this derivative equals to 0. Okay, if I have this expression equals to 0, so you know that I can add by this term to each side of the expression to have root of 4 minus b squared equals b squared over root 4 minus b squared. Okay, now I can multiply by root of 4 minus b squared, root of 4 minus b squared. So simplify it here, and now what I have is that this is to the second power, so it will be 4 minus b squared equals b squared. Okay, and basically we need a new page. Okay, and basically we just can add by b squared. So what do we have? We have 4 equals to 2b squared, and now I can divide by 2. So b squared equals 2, and b is going to be the root of 2. Okay, so we have root of 2. So b is going to be the root of 2 according to this process. But what we did, basically what we did was just find the area, find a constraint, represent the area in terms of one variable, differentiate the area, set the area equals to 0, and find the dimension. Now, you know, the problem is the algebra, not the calculus. But essentially, what we have here is that the root of 2, b is going to be the root of 2, so h is root of 4 minus b squared, right? So h is going to be root of 4 minus square root of 2 to the second power. So h is going to be the root of 4 minus 2, so h is going to be the root of 2. We got that h should be the root of 2. So essentially, what we find out is that the maximum area, the rectangle inscribed in a circle that has the maximum area, is a square. This is what we found with this expression. So what are the dimensions of the rectangle who has the maximum area? Is going to be a square. And that's it. This is an example of optimization. We found out maximum area with this. Now maybe you may ask, hey, but how do you know that this is the maximum area and it's not that different? You can use the first expression, ab root of 4 minus b squared, to test if it's a maximum area. Okay? So what you can do is to set what is the area when b is root of 2. Root of 2, we know that this is root of 2. So the area when it's root of 2 is going to be 2, right? Now, what's going to be the area for a value that is closer to root of 2? So we're going to set it for area for 1. So b is 1, root of 4 minus 1 squared. So we got the area is going to be root of 3. Okay, and now we're going to find out what happens if the area is 2. If the area is 2, we have 2 root of 4 minus 2 squared. We got 0. So look at that, area at root of 2 is greater than area at 1 and is greater than area at 2. So it means that this function, if it's smooth, is in this form. We have here 1, we have here root of 2, and we have here 2, right? So we have a maximum. If you get these two values greater than the third, we will have a minimum. And this is how you can find the relation between maximum and minimum area. Okay, so what we did? Essentially we did 4-5 steps. First, find the relation or the function that relates variables. Second, constraint, in order to have the function in terms of just one variable. Third, differentiate, apply the table of derivatives. Third, set the derivative equals to 0 to find maximum value. Solve the expression, and finally test if it's a maximum or a minimum. Thank you for being here. I hope that you enjoyed this video, that you like it, and if you need more videos about calculus, just let me know. I'll explain you how to do it. See you the next time. Bye bye.